Okay, that brings us to the position equation, which looks like kind of a beast, but it's really not that bad once you get used to it and understand what all the parts mean. Let's go back over to the clipboard so I can walk you through it. So this is the position equation. It is on the AP gouge, and I'm going to show you how it looks on the AP gouge. So, okay, now first a bit about terminology here. In the last video, I showed you that the initial position is, we use a little letter I. And I kind of forgot that our book and College Board doesn't use that convention. That's the other book. Um, from here on out, we'll be using this little zero. Okay, so X, that little circle, is a zero, meaning the position at time zero, or the velocity at time zero. And the way we say this is not. N-A-U-G-H-T. It's the highfalutin British word for zero or nothing. Um, so we call this X naught or V naught. Okay, so let's define all these terms. So this is the final position, and this is going to be in meters, and it has to be from some reference point. So to be able to use this equation, we have to have an established reference frame, and it will tell us the distance from whatever we've defined as the origin. Okay, X naught is the initial position, initial X. V naught t is the initial velocity times the time that velocity lasts. So what this equation is for is to figure out the final position of something after some period of time has passed, when it's moving or not moving or accelerating or whatever. And this time in seconds is how long a time interval we're looking at, how long the time interval we're interested in. 1/2 is just 1/2. A is the acceleration of the thing, acceleration. And as you know, that is in meters per second squared. And t, again, is the time in seconds. But notice that in this term, it has to be squared. We have to square the time. So I'm going to say that times time squared. Exclamation point, exclamation point. Very common error to forget to square this time. You got to square the time. Okay, so for example here, say we roll through a stop sign. We're in a hurry to get where we're going. So we roll through the stop sign at 2 meters per second. Then as soon as we pass the stop sign, already moving, then we accelerate at a rate of 2.5 meters per second squared for 6 seconds. And what we want to know is how far from the stop sign are we at the end of that 6 seconds. Okay? So if you're doing this for homework, we do the given information. So V naught is equal to 2 meters per second. Acceleration is equal to 2.5 meters per second squared for 6 seconds. And that's basically all the information that we need. Now notice we're measuring from the stop sign. So that means we can consider the stop sign position 0, and this, the initial position, will be 0. So that part's just going to fall out. Okay, so the equation we're going to use, I know I have it written right here, but when you do your homework, you're going to want to have it written out. So you're going to write XF is equal to X naught plus V naught T plus 1/2 AT squared. And then we'll do the work where, oh, I didn't even put in the find. I forgot the find. Okay, so find delta X. How much the position has changed, how far we've gone. And that's going to be in meters. Okay. Anyway, now the work. So we're going to start plugging values into our equation, because we're just going to use this as like a template and just plug values in where they go. So we're trying to find the final position. So XF remains as XF. The initial position, X naught, is 0, because we're measuring from the stop sign, plus the initial speed, 2 meters per second, times 6 seconds, plus 1/2 times the acceleration, which is 2.5 meters per second squared. I'm going to run out of space here, but not by much. Times 6 seconds, and that 6 seconds is quantity squared. There we go. We made it. All right, let's slide over here a little bit so we stay off my face. So now we can start consolidating this. And we get XF, the final position, is 2 times 6 is 12. Seconds cancel. So that's 12 meters. Plus 1/2 times 2.5 times 6 squared. Whew. Maybe we can do that in our head. Maybe we can't. But 6 squared is 36. Tell you what, let's just get a calculator out here and do it. We can do that in our head, but why show off? So 6 squared times 2.5 divided by 2. Don't forget that 1/2 in there. So that is 45 meters. Okay? Because we have squared the 6 seconds. So this is 36 seconds squared. We have to square everything inside those parentheses. So since it's 36 seconds squared, those seconds squared cancel the second squared in the meters per second squared and leave us just with meters. So it all boils down to 45 meters for this term. Add them together and we get 47 meters is our answer. Okay, we wanted to know how far we went in meters. We got an answer in meters and it's all good. So you may have noticed this as I'm going through it, but each term in this big ugly equation turns out to be meters. The initial position is the position in meters. The velocity is meters per second times seconds, did that one. And the acceleration term is meters per second squared, but when you square the time, the seconds squared cancel out and leaves us with meters again. So each term boils down to meters. That's the point. The other thing, and this starts to make sense of it, is this handles all of the possibilities that could happen to the object that we're watching. The first one is where it started. We have to take that into account. If we didn't start at the origin, we want to know where it wound up, then we have to know where it started relative to the origin. This term is what its initial velocity does to it. Because if it's not accelerating, it's just rolling along at a constant speed, it's going to end up someplace other than where it started. So this handles the initial speed. And then if the speed changes, it accelerated, then this term handles the acceleration. Okay? So yeah, so it comes out to be 47 meters. Now, what if we did not roll the stop sign? What if we came to a full stop and then proceeded forward? How far would we go in that case? Well, in that case, the initial velocity would be 0. This term would drop out. We'd have 0 velocity times some period of time. So this would be 0, and all we would be left with is just this one, and we would have gone 45 meters. Now, conversely, what if we didn't accelerate? What if we saw a police officer watching and we said, uh-oh, and kind of froze up and just kind of rolled through the intersection at our 2 meters per second? So this is valid, but we don't accelerate. Well, in that case, the acceleration is 0, and this term will drop out. And then in that case, our distance would be 12 meters, and acceleration doesn't do anything for us. Okay, and that's what you'll find as you do these. It's actually pretty unusual to have a problem where you have a number for the initial position, for an initial velocity, and for an acceleration. Usually one or more of those is 0. Okay, right, so that's it. Okay, so yes, we described motion, we talked about acceleration, we defined it, we had an equation for it, and we talked about the units that describe it, which is meters per second squared. And yes, it's very important that you remember the units of acceleration are meters per second squared, or meters per second per second. Say it however you want, but you got to keep them in there. We looked at position versus time graphs and velocity versus time graphs. We found out that the slope and sometimes the area underneath those graphs means something that is useful to us. And finally, we got our first look at the position equation, which looks ugly, but usually parts of it drop out and it's not as bad as it looks. Okay, hope you found this helpful. This should get you through the first homework assignment, and we will see you next time.